参与。哎，我赫然发现，我材料力学这堂课竟然是台积学生的一个要求的课，哎，我整个很压抑，哎，啊，怎么了吗？哎呦，竟然我的那个是台积学生课，哎，真棒。嗯，I found that my mechanics of materials actually is a kind of is included in TSMC module. Wow, I'm surprised. I'm surprised. All right, so let's continue. Okay, let's continue. I hope. Sorry, I need to check. Okay, let's continue. So last week we talked about how to draw a Mohr circle. Mohr circle is really important. That it's a really comprehensive, easy way, easy to understand for you to draw the stress component in all the inclined section. Okay, so the only thing is a little bit difficult to understand is that this one, tau x1 y1, positive tau x1 y1, point downward, positive point downward, which is different from what we usually know, because we want the angle change, rotation of angle in the real world match the Mohr circle world, okay, Mohr circle space. So if you can see that when we rotate our x1 with theta, and in this space, it rotates 2 theta, but within the same direction. If we using this direction, well, it may not rotate in the same way, in the same direction. So that's the reason why we try to make tau x1, y1 point downward as positive, because we want to match the rotation. Okay, so that's the most important part of it. And we firstly, because we talk about plane stress. So our plane stress will force this sigma x1 tau x1 y1 origin at the x axis, sigma x1 axis. So you can see sigma x1 equal to sigma average here, and you can set the origin of the Mohr circle. Okay, and then you have R. The R will be the differences divided by 2 squared plus tau xy square plus them together and square root. Okay, so actually I know what's that stand for, because this is the oblique edge of the triangle. Okay, vertical triangle, 90 degree of triangle. Okay, so that's it. And then each point in the circle space represent a plane in the real world. Okay, and the plane, the two planes, the angle between two planes, if it is theta, it will become 2 theta in the circle. Okay, so you can see this green plane has the point in this one, and blue plane is here, so they have 180-degree in circle space and in 90-degree in the real space. Okay, so that's it. So yeah, and also if you want to try a new inclined section, you can see this is theta d. Okay, theta d means that theta 0. Sorry, theta 0 means that you can start from the plane A or point A with 2 theta 0, and then you can pinpoint the plane D located in the circle in this dot point, and then you can just draw calculate the coordinate of this D, and then you can get sigma x1 and tau x1 y1 just purely using triangle, sine, cosine, and geometry problem you can solve in junior high school. Okay, so everything becomes simpler. And principal stress, you can imagine that the greatest maxima sigma x1 and minima sigma x1. So this is the 2 points on left-hand side and right-hand side of the circle. Easy. Okay, and then you can also calculate the theta p divided by 2. Okay, and you can see the original point A to the sigma 1 point, sigma p, and then you can see they have the angle between in the circle space divided by 2, and it's a real theta p. You can obtain that. So everything can be obtained by Mohr circle. And then we talk about maximum shear stress. You can imagine that where is the maxima and minima stress? Of course, this place, right? Here is minus tau maxima. Don't forget minus, because upper point upward is negative in tau x1, y1, right? And so you can see that tau max is actually a value. Okay, it's not a symbol, it's a value. So this is tau max. So yeah, you see the tau max is actually equal to R, right? And then this is theta 0 degree, and this is theta 90 degree. And of course, you can obtain 2 theta s by just getting this pie chart, okay, pizza shape. And then you can get, you see this one is theta 2 theta p, right? Because in your previous page, you know this one is sigma 1, right? So this is 2 theta p, and you see 2 theta p, and between the theta p and theta s, it is 90 degree. 90 degree divided by 2, 45 degree. Okay, and you see this sigma p, sigma 1 go up sigma 90 degree and go down 90 degree. So which means that theta s equal to theta p plus 45 degree or minus 45 degree. Everything satisfied just right, right? Very good. 这样听得懂哈？这边就是主平面发生的地方，然后这是最大剪应力跟最小最大剪应力跟最小剪应力发生的地方。你看它们之间永远在圆的里面都差90度，那不就是在现实生活中差45度吗 ？OK。Right, so if you can accept that, we can straightly use the Mohr circles to determine the stress acting on the element at theta 30. Okay, but this is just, we haven't given you a problem yet. I'll give you now. Sigma x 90 MPa. And this is sigma y 20 MPa. And there's no shear. Okay, no shear. So now we can straightly obtain the Mohr circle. Okay, this is sigma x1. This is tau x1 y1. Okay, and then how can we determine the origin? Easy, right? Sigma average equal to 90 plus 20. Be sure the value, the negative or positive sign, okay? 5 MPa, okay? and R equal to the difference 90 minus 20 divided by 2. Ooh. Divide by 2 minus plus 0 square, right? Because there's no shear. And 35 MPa. Okay, so can I move around? To save some space, I'm sorry. Okay, now we are ready to set the point. So this is 55, right? 55. Okay, and 35 will be our 35 will be our R. So what is R? Let's try 35. Maybe too big. How about this one? Okay, let's try it. Go. All right. Right, this is 35 radius and 55, okay? And now you've done that. Let's try, and also, yeah, let's try it. And you see the green, this is easy. This one is really easy. So this is green, plan A. Where will it be? Ta-da! This is really easy beginning. All right. So A equal to A point theta equal to 0 degree, and this is accidentally plan. Sorry, principal plan. Okay. And that's it. So actually we done that. Now the question is, what about the stress at the theta equal to 30 degree? And also we want to draw the stress element, right? Okay, so theta 30 degree. So theta 30 degree, how can we do that? So you see, it will start from this x1, x, and go for 30 degree to get the x1. So 30 degree in the real world, what will it be in the space world, circle space? 60 degree, right? So 60 degree. And then you can get the point. Suppose it should be D, okay? And now I will give it the blue color. And how can we get that? We can actually using a triangle to help us to get the value. Okay, so sigma x1. The sigma x1 here will be the blue point D coordinates. X1, sigma x1 coordinate and tau x1 y1 coordinate. So it becomes completely a geometry problem. Sigma average plus R cosine 60. Okay, so it's 5 plus 35 cosine 60 degree equal to 72.5 MPa. Okay, and tau x1 y1 will be R sine 60 degree, right? However, don't forget, we just get the geometry problem. We need to get the real value of the coordinates. And the upward will be negative in tau x1, y1. Okay? So we need to be careful. Equal to minus 35 sine 60 degree minus 30.3 m pa. Okay. So here it should be theta equal to 30 degree. And we know that this is 30.3. Okay, the height is 30.3. But you need to get the minus sign because it's in the first完蛋了，象限我忽然不知道怎么讲，象限怎么讲？不是 dimension， quadrant or something， 象限，第一象限不是 quarter， 但是我记得是 core 什么 something，upper right angle upper right region. Anyway, you know. And then next one. So now we can draw. Hey. Okay, this is square. Okay, and then this is x, and this is x1. So this is x, this is x1, and this is 30 degrees. So stress element here is 72 and minus 30.3. Okay. So this is 72.5 MPa, and this is 30.3 MPa. This is 72.5 MPa, and shear is come in pair, in group, right? Oh. Okay. 30.3 MPa. Right. Are we done? No, because we don't know the y1 axis. So can we do that? Of course we can do that easily, right? This is your, so now you see here is the blue plan, which is plan D. Plan D, okay? And here is your plan E, all right? Right. So where is your plan E? 90 degree in the real world. How about in the circle world? 180 degree, right? So 180 degree. Connect then. So can we do that? Can we get the coordinates in this? Of course we could do that. We have another triangle here, right? And again, 60 degree, right? So, and this is E point. So because we are going to get the theta equal to 120 degree, and so sigma x1 equal to 5 minus 35 cosine 60, 37.5 MPa. Okay, so this is a positive, this is a positive, and 37.5 MPa. 37.5 MPa. Done. Okay. Don't you think it's easy? I think Mohr circle is a really smart way to make everything we taught in chapter 7 before, easily. I mean, illustrated in a really simple way. And it simplified the problem into a geometry problem. Okay, very easy. 哇，今天的风好舒服哦，太凉了。你知道我非常需要风，如果没有风的话，我觉得很痛苦。就例如说在健身房啊，我也希望那个电风扇都是直吹着我的，对啊。但很多人不喜欢嘞，很多人不喜欢电风扇直吹的自己。哦，你看这样好舒服，对，太棒了。Okay, so I guess it's done here, and then we have a classic sample in the next page. Okay, this is kind of a special case. This is a really easy problem. Next one is a classic. So you can sort of find out all the problem type in the next one. All right. I think of a really smart way to save my time. Next one, go. Right. So this is not 90. This is no. So this is 50. And it is compression. Sorry, compression. And this is positive. And this is 10. Okay. And there are several shear upward, downward, right? And this is 40 ampere for the shear. Okay, so this is the problem, right? This problem is a 50 ampere for the compression. Y direction is 10 ampere for tensile, and shear for 40 ampere. All right. Again, let's write down, get the sigma average. Sigma average equal to minus 50 plus 10. Okay, you see that the reason why I didn't write down this is sigma x equal to 50. No. It's sigma x equal to minus 50 and plus 10 divided by 2 average, right? So this is minus 20. Okay, so you found that this is a little bit different from the previous one. R equal to minus 50 minus 10 divided by 2 plus 42. Sorry, square 50 ampere. Okay, now we are ready to obtain the sorry, I prefer to write down here. All right. And let's write down the sigma x1. Okay. And you notice that sigma average is minus 20. Oh. Okay, so this is tau x1, y1. Okay, and minus 20 will be your origin, right? O. And your R is 30. Okay, so your circle looks like this one. Oh, perfect. Okay, that's it. So you see 20, 30. Okay, so you notice that this origin is actually go to the left-hand side. Okay, it is possible, right? Now, this is a little bit tricky now. We are going to get the point A, but we don't know. So let's get, so for example, we, you can see the A here is, where is the A? Where is A? We notice that this is minus 50 and this is minus 40 ampere. So actually, its coordinate is also like, well, another 30. Okay, and this is 40, right? So this should be A. Can you follow me? Can you get my get what I talked about? You see, this is O, and we set, after we set, we need to next set point A. The point A in this space, the component, the coordinate component is actually the value of these two values, right? So here is minus 50 and minus 40. So minus 50, 20, 30, right? And minus 40. So you can set point A here. And point A represent theta equal to 0 degree in the real world. Okay. Now the problem is, what is the value? What is the value of this angle? Because we will use this angle quite frequently later. Okay, so how can we get this red angle? And we name this point P2, all right? I know, but I believe you know that because it's a principle 2. And this, of course, this is P1, right? So let's take, how can we get AOP2 angle? Can we do that? Yes, actually we can do that. We can follow the tangent AOP2, which is equal to 40 divided by 30, right? Dana, dana, dana. So tangent AOP2 angle equal to 40 divided by 30. And then we can get angle AOP2 equal to 53.13 degree. So now we get that 53.13 degree. All right. Not too difficult, a little bit difficult. And then DOP2. What is DOP2? D, where's the D? Oh, next one we're going to get DOP2. Where is D? What is D? D is the first question. Stresses at theta equal to 45. So they are asking 45 degree. X1 is 45 degree. Okay, and okay, so this is 45 degree, and yellow, okay? Yellow. And this is D. Let's give the name of it. D, all right? And then, so we're going to get stresses at 45 degrees. And we just need to see the point. And you see this rotate to counterclockwise 45 degrees in the real world. How about we rotate how much in the circle world? 90 degrees, right? 90 degrees counterclockwise. So it's 90 degrees here. Okay, 90 degrees. So this is D. And in the real world, this is theta equal to 45 degrees. All right. And of course, this angle is easy, right? Which is DOP2. DOP2 is 90 minus 53.13, and it gets 36.87 degrees. So 36.87 degrees. That's it. All right. And then we are ready. We're sort of ready because we are ready to get the value of this. Okay. We want to get the coordinate of the D because we are going to get the theta equal to 45 degrees, which is point D in the space, in the more circle space, x1 equal to, all right, you see, what is the sigma x1 axis coordinate of point D? Minus 20 minus 50 cosine 36.87. I guess this is junior high school level, right? Right? Minus 20, and minus 50 cosine 36.87. So these two lengths adding up together is the sigma x-axis coordinate for point D. And this is minus 60 m par. And how about tau x1, y1 value? Easy. R sine 36.87 degree, 30 m par. And remember that the value you get 30, this is 30, right? This is 30 downward, so it's positive. So again, you are ready for 60 is minus. Okay, minus 60 m par. And this is 60 m par. And 30 m par is positive, right? So yellow plan D, 30 m par. Okay, and come in pairs, right? Come in pairs. So this is 30 m par. All right. So are we done? No, because we haven't done the blue plan. And blue plan in real world 90 degree away from plan D. How about in a circle? 180, right? 180. So this is the, sorry, this is let's say E, and this is plan E. Okay. And yeah, how can we get there? How can we get the sigma x1? So theta equal to 135 degree. Theta equal to 135 degree. So sigma x1 equal to minus 20 plus 50 cosine 36.87 degree, 20 ampere. Okay, 20 ampere is positive. So it is positive 20 ampere. 20 ampere. Okay, done the first bit, right? So everything become geometrical problem. And all you need to do is step by step and make sure that tau x1, y1 downward is positive, and make sure that the circle you travel, the angle opened in certain direction, you just double it in the circle world. That's it. Everything just done just like that. Are we done? No, because we have two extra problem: principal stresses and maxima shear stress. And we are okay, because all we need to do is copy this one. We copy this one and we pass to the next page, and then we can simply get the principal stress. Right. I think it's quite easy for chapter 7. Chapter 7 is, once you understand that, everything become just step by step, right. 最近我在忙整理我的爸妈家，我把我爸妈接过来新竹住，然后我后来就发现一件事情，就是环境是非常重要的。环境，我以前小时候都不觉得环境很重要，但是我后来现在发现，环境才是决定一个人的生活跟习惯，然后会不会成功，真的很重要，真的。然后会不会健康的活下去，真的是非常非常重要。所以以后你可能就知道了哦。对，要注重自己的环境。啊，没事，之后这个很难讲，不能，没办法三言两语讲完，尤其是在我赶课的时候。下一个 ，next one. I just talk about environment is really important for a person, for a human being. Okay. Pass. Continue. Okay. So next one is principal stress. Principal stress. I believe you know principal stress. The first one is P2, P1, and the other is P2. So how about P? Okay, so next one. That's a. So we can just directly get that. Wait a minute. Oh. Theta P2 equal to 53.13 divided by 2, right? So 26.6 degree. So you see, in the circle world, it go 53.13. So in the real world, divided by 2, 26.6. So which means that you have a 26 points. You have a 26.6 degree. Okay, in this, and Okay, so this is your stress element look like, and what is the value? What is the value? Easy, right? 20 plus 50. 20 plus 50, 70. 70 in the negative sign, negative part. So here is 70. 70. Let's put not degree, m part. And this is 70 m part. All right, easy. How about y1? Y1 is also easy. It's not y1, p1. P1 is also easy, 30, and it's positive. We just look at the circle and everything, we obtain the value. So easy. Okay? And that's it. That's it. Principal stress. Tau max. Again, tau max, you know where it is. Tau max. And this is minus tau x. Right? And then you know the value of the theta s. Because in the circle world, 2 theta s equal to 90 degree plus 53.13 equal to 143.13 degree. All right, so your theta s is actually 71.6 degree. Okay, 71.6 degree, and then you can get a okay, so x x, and this is 70 x1. So this is a 71.6 degree, and you have a okay. Okay, and then how what will it be? The pink one, pink. I give you a pink max point, and the real world in this 71.6. All right, and what is the value? Tau max. Tau max is positive R 50. Wow, 50, 50, 50 ampere. And of course, it is come in group, right? So this is 50 ampere. Okay, so is that done? No, because when the maximum shear stress occurred, we still have sigma x1. Unlike principal stress, if principal stress occurred, no shear stress. You see, they are all on the tau x1, y1 equal to 0 axis, right? So, what will it be? Let's take a look. What is the sigma x1? 20. So this is negative 20. Negative 20. 20 ampere. 20 ampere. 20 ampere. And how about the other one, the other surface? How about this one? This one will be in this position. And how about their sigma x1? Again, the same 20, negative 20. 20. 1t. So don't you think this is easy? We didn't talk about what is the maxima. We didn't do the differentiation. We don't do the tangent edge. Sorry, tangent and cosine or cotangent or something. We never. We don't need to do that. All we need to do is just draw a circle, and everything just appear. This is fascinating. Okay, 10 minutes later, we will have a. Well, I will see you tomorrow morning. 10 minutes later. Okay. Then we are going to talk about Hooke's law. Hooke's law in a plane stress case. Not difficult, right? I hope. 时间过超快的，一下一学期就结束了，我们又老了半岁。而且年纪越大，真的时间过越快。我不知道我们跟大家讲过这个理论，就是为什么人家会说年纪越大，时间过得越快？因为我们的反应变慢了。我们的反应变慢，我想一句话，可能以前要想1秒，但是我现在就要想3秒，但是我还是以为我想了1秒，所以我整个24小时就变成除以3这样，真的是真的，我真的是这样觉得。好，然后你看哦，鸟跟狗跟猴子那些，你看它速度多快，眼睛，你看它动就这样，所以它们的寿命就很短。但他们感觉起来跟我们活的一样长，感觉起来跟我们活的一样长。那你看那些乌龟，你看它爬得很慢，然后它其实跟我们活，它感觉起来跟我们活的一样长的时间，但是实际上它比我们，我说真实的时间却比我们长。所以我真的是相对论诶，其实时间根本就是看你的感觉来想的。Anyway， 好，下一个 Hooke's law for plane stress. So strain due to plane stress. We are talking about a volume here. And we substitute to sigma x, sigma y, and tau xy, tau xy. And so normal strain, okay, in x direction. Again, I guess you know that, your epsilon x normal strain in x direction has 2 contributions. The first one is due to the sigma x tensile. Okay, so sigma x divided by E, no problem. You know that very well. However, don't forget your sigma y. The sigma y is a tensile in y direction. However, it will provide the Poisson ratio to compress to make the lateral strain shrink. So it's minus nu sigma y, right? So this is kind of this is the first contribution and second contribution. Epsilon y is also the same. Sigma y minus nu sigma x. No problem. It looks like exactly the same. However, because this is plane stress, there are no stress in z direction. So you see nothing in z direction. No. So the z direction only has the Poisson ratio from x and y. Okay, so you see this is sigma x and nu divided by E, and sigma y, nu divided by E. That's it. So you see this is a little bit different from Z, is a little bit different from other. And I want to give you a really important emphasis on this epsilon at z. Sometimes your seniors always think, plane stress, no stress in z direction. So they assume, they think no strain in z. Is that correct? No. Plane stress means no stress in z direction. We didn't say strain z is 0. Okay, so you see epsilon z is non-zero because of the Poisson ratio due to sigma y, sigma x. So be careful about this, all right? Don't mix it up. Then shear strength, very easy, tau xy divided by g gamma xy. That's it. So yeah, this is easy, and this is relatively difficult, and this is important. Sometimes we easily make mistake here. Then we can think epsilon x, epsilon y, epsilon z. So if you think, so the epsilon x, if we all subject it to a positive sigma x, positive y, positive tau xy, you see the x will grow, right? Will grow. And y will grow either, y will grow too, but z will shrink. Z may shrink or not, but you see here's minus sign. So if I draw positive, it's okay. We just apply negative, it become shrink. So we just see that, okay, the volume change for generally for this blue element is epsilon a times epsilon x. This is a is the original length. B original length times epsilon y. C original length times epsilon z. And then you will see the differences of the volume later. Okay, and also we see that shear strength and normal strength are independent. They don't mix up. They don't mix up because epsilon x, y, z is kind of, actual axis, but shear strength is just changing the angle. So they are kind of, we can kind of make it independently, treat them independently. All right, so next one. Some example of Hooke laws for plane stress. So you see two axes, which means that sigma x non-zero, sigma y non-zero, tau xy equal to 0. And right, so this is epsilon x, epsilon y, and you see actually these three equations from in previous page. All right, and if we combine together, this one, and we can obtain sigma x and sigma y in this form. Well, you're just changing the position to the left-hand side or right-hand side. Easy, nothing important. So what I want to address is here is that this one you just learned in the previous page, you just learned is a general case. This is a special case. The next one is even special case, uniaxial stress. Only sigma y, only sigma x is non-zero. So epsilon x equal to this one, and yz is Poisson ratio. So everything is, you learn that in chapter 2. Okay, and pure stress. Yeah, this is okay. Right. Next one, I'm going to 2 minutes. I'm going to introduce the figures that I just introduced. A is B, C are original length in x and y and z direction. So A times epsilon x is the displacement in x direction. B epsilon y, the increment of in y direction, and C's epsilon z is the increment or decrease, I don't know, in z direction. So the original volume is A, B, C times together. V, no problem. How about V1? V1 is A, B, C, 1 plus epsilon x, 1 plus epsilon y, 1 plus epsilon z. You see, yeah, you can see A plus A epsilon x. So this is what you get here, right? And B and C. So you all times together, and you can get this long volume. This is a volume after the deformation, V1. And then, because in the mechanics of material, we assume the strength are small, right? In our mechanics of material. So when they times together as the second order, even third order, we can neglect it. So our V1 will approximately ABC1 plus epsilon x plus epsilon y plus epsilon z. So yeah, the change of the element under a really tiny small strand is ABC times epsilon x plus epsilon y plus epsilon z. Okay, and if the change per unit volume, so you just divide by V naught, ABC divided by that, it will be only the epsilon x plus epsilon y plus epsilon z. So wow, you only need to know the number of epsilon x, y, and z, and you know the change per unit volume. 体积改变率，你只要去看，把它相加起来就好了。三个轴向的单位的应变加起来，就是这一个元素它的体积改变率哦，蛮酷的一件事情。Okay, I guess that's it. I will see you tomorrow morning, and thank you for coming. Any question, just come here. 请问
这个 Q 等于 Y 底耶，它这个 Y 到底
是它好 QY 底 A 其实就是这一个面积，这个面积它的行星到中心轴的距离乘上它的整个面积，对，就是所以这个 Y 其实就是它每一个位置对于中心轴的距离，积分是什么意思？
那为什么会变成就是上面这一块，然后乘以到中心轴？
就是上面这一块的每一个点到中心轴距离，每个点到中心轴距离，每个点到中心轴距离，然后积分起来就是这个 Q。
那我不用管下面这一块。
好，其实你也可以管，你也可以用下面这块哦。你这两个上下两个值算出来是一样的哦。你用上面的 Q 算出来，跟下面的 Q 算出来，答案会是一样的。其实你想想看哦，这个东西弄上去，就是它下面是负的 Y 哦，所以说它这边会抵消掉，这边跟这边会抵消到，结果你发现下面的跟上面的其实长得是一样的。
哦，所以不用看到这一块，
不用看到这一块
抵消。
对对，应该说我们之前为什么要留上面那块，是因为我们要知道这一个面的 shear stress，所以我们才把它切掉啊。对啊，所以我们切了留上面，所以我们才管上面的截面积。但是如果你今天切留下面，那也可以啊，你做出来会一模一样。对，大概是这样。
那我为什么留上面这样子的面积，不是看这个中心轴上面的面积？
因为我们要知道的是这边的 shear stress 啊， 所以我们不是说我们每次说要切到，我们要看那个值的时候，我就是切掉以后，要么就留上面全部，
所以
要么留下面全部。
看它很正。
对，因为我只要看水平的 shear stress，因为成对出现，所以我们也可以看它，就这个就等于算它的 vertical 的值，这样，没问题，没问题。
前面像这，我要怎么知道它的 y 到底是正的还是负的？
中性轴以上就是正的，中性轴以下就是负的。
正的。那它为什么就是像它这边好像还可以理解中性轴上面是正的，可是中性轴下面是负的，但是它等到换到作业的像第一题这种，我就有点不是很懂，我要怎么看它的 y 到底是正的还是负？因为好像它的规则就反过来。
这 maximum normal stress 没有啊，没有啊，为什么会反过来？
所以还是一样是看这一条，但是这里是它的中性轴，所以它
中间中性轴
中间是中
是这个哦。对，是这一个叫做中性轴，所以中性轴以下是负的，中性轴以上是正的。
哦，所以它的中性轴以
对，
下
在这里
是这一段
不是
吗？
中性轴以下是，这一段
哦，
这边就是负 y 多少？
嗯，
负二分之 t。
可是我要算sigma的时候，
嗯
它不是会有我这样凹，它不是上面会是 compression，下面会是
对
tensor，
对
那我带 y 带正负，不是其实就没有差，它就是一个
的确是，但是因为如果你是降凹的话，它是曲曲线，所以 m 是负的，所以会造成下面是负 y 的话，我看一下，负 my 除 i 嘛，所以负的 m 跟又是负的，所以它就是负的，然后就是 compression，下面变成 compression，上面变成
负的 m，可是 y 又是负的，这样子应该是正的。
不好意思啊，负 my 除 i 嘛，已经有个负咯，然后你的 m 又是一个负，然后 y 又是负，所以负，所以就是真的负，所以表示说下面是 compression。对，
可是他要我算 sigma 的时候，我怎么知道他要我算的是上面的 sigma 还是下面的 sigma？
他说top 或 bottom，所以就是上面的 sigma 跟下面的 sigma 都要算的意思吧？
所以就会是正的跟负的。
多算一次吧，我猜他说 What is the maximum normal stress at the top and bottom？你多算一次啊，
他会跟你说要。
对，第五章很难哦。不过，我也有时候我觉得很有趣。我在念书的时候，我也觉得超难。然后我也都会写题目，但是但没有那么的通。最什么？最什么？最知道在干嘛的课？所以你的意思是说，